Yeah,
maybe I have to
yeah.
factor
So
in those.
maybe for time's sake and lecture, I do want to answer your question for sure. I want to take the time to do that, but probably not now.
I understand.
Yeah,
I was
sure.
just wondering if it's better email or answer.
Um, you could ask right after class, after the quiz, or email, whatever you prefer.
Cool, thank you.
You're welcome. Okay, so we're going to move on to volume. So we kind of gave a little preview last time. Volumes of solids, here we go. So using integration or accumulation to calculate volume means we're going to form an empty shell from a curve. I'll show you this in a second. So we're going to form an empty shell, and then we're going to fill that shell with right cylinders and track the amount of the empty shell that's filled as we go, and that's going to be a volume net accumulation function, right? So as either x or y increases, and we're going to be filling up the shell with these cylinders, we'll track how much is filled at any given moment. That's a volume function, right? That'll be a volume accumulation function. Okay, and so like we've been hammering all semester, if you want to write an accumulation function for a quantity, you need the rate of change of that quantity. So if we can figure out the rate of change of volume for these right cylinders as they're growing in the empty shell, if we can get the rate of change of those rate of change of volume, then we can just write down the volume accumulation function because we already have our template, right? We have our base net and total accumulation functions that all we need is the rate of change of whatever quantity we're talking about, and we have the accumulation function. Okay, so let's just let me give you an example here. So here's taking part of the sine curve and making an empty shell. So watch that again. So I'm gonna rotate that sine curve around the x-axis to form an empty shell. And then after I do that, I'm gonna fill that shell with cylinders. And as the shell is getting filled, we're gonna track how much volume has been filled so far. So that's exactly building a volume accumulation function. Okay, I could take that same curve and I could rotate it around the y-axis. Makes a totally different shell, right? So same curve, like half of one cycle of a sine curve, rotated around the y-axis, totally different kind of shell there. So this is a whole new ball game, even though it starts with the same curve. And so then I'm going to take that and I'm going to fill it with shells. And keep track of how much of the shell has been filled so far. And that's exactly a volume accumulation function. If I want to know the total volume of the shell, then I just evaluate the function at the last value of x, right? So if I come out here and evaluate the function at the last value of x, that gives me the volume of the filled shell. Okay, so right cylinders. So if you look at your handout.
I'm sorry, I just have one question from that animation.
Yeah, sure.
Are those, from the last animation that you showed us,
Uh-huh.
are those cylinders being stacked onto each other, or how did you create that dome on the inside? Is that
So the dome came from the empty shell. I just took the sine curve and rotated it around the y-axis.
uh-huh.
That creates the dome or the empty shell.
Okay, and then those cylinders that we're adding, are those
They're like nest. We're gonna do this example later, but they're like nested within each other. Okay. So like, let's see. So each cylinder is encapsulates all the previous ones.
Oh, okay.
Do you see that?
Mm-hmm. Yes.
Yeah. So they end up being nested. Like each one gets nested by the next one.
Okay. Thanks.
Sure. Okay. So what's a right cylinder? So let's talk about right cylinders. A right cylinder, and this is at the bottom of page 1 of that handout from Wednesday. A right cylinder is you can start with any surface. So like this. So that's like kind of like a trapezoidal triangle thing with a hole in it. Start with that, and then if you extend it perpendicular to the plane of that surface, just keep extending that same cross section. That creates a cylinder. So cylinders do not have to be circular like a tin can. You can start with any region, and just sweep it in a direction perpendicular to the plane of that region, and all the points that are swept out in space become, so this is like some kind of trapezoidal cylinder with a hole in it. Okay? So just a square bar. That's an example of a cylinder running this way. So that this cylinder runs kind of up and down. This cylinder, if our initial cross section was the square here, then you just extend that perpendicular to the square. That creates a cylinder. Okay, so a cylinder is any shape that you start with, any region of any shape. It can have holes in it. It can be any shape. Extend it perpendicular to the plane of that region, and you get a cylinder. Now, the cylinders that we're going to be dealing with the most and filling up these empty shells with are this type. So this is a right cylinder, and these are the ones we're going to be using to fill up our empty shells once we make an empty shell. And so that cylinder can vary in two different ways. It can vary in height. So this is that cylinder varying in height. Or it can vary in radius. So there's that cylinder varying in radius. Again, vary in height. Or the cylinder can vary in radius. And so we're going to get a different rate of change in each of these cases. So we're going to have a rate of change when the cylinder varies in height, and we're going to have a rate of change when the cylinder varies in radius. So we want to figure out what each of these are, right? Because this is the whole ball of wax. In order to write volume accumulation functions, we need rate of change of volume. So for each of these two cases, we're going to figure out the rate of change of volume. So whether growing by height or growing by radius. Okay, so let's do that. So if you flip over to page 2 of your handout, it looks something like this. And I want to so many things on the screen. Okay. So at left is a cylinder and the necessary measurements for this question. Okay, so it has what? It has an interior radius. The hole has a radius of 2.5 meters. And the outer radius is 3 meters. And the height is 7 meters. So we're just going to use these values to work out an example. So let's first express the volume of this cylinder. So what would the volume of this right cylinder be? Or what would the structure of that be? Like, what would the structure of that formula be that would get us the volume of this cylinder? Meaning all the gray stuff, right? So all the gray stuff is the volume, right? So this hole that I could put my hand through does not count as volume. Only the gray matter around the ring there counts as volume. So she said pi r squared, certainly going to be involved here. So pi r squared is certainly going to be part of it.
So would it be pi r squared of the big circle, so one with the radius of 3 minus the little circle, which would be the radius of 2.5?
Okay, so that's good. So it's like the bigger radius, pi r squared, minus the pi r squared for the smaller radius. Now, will that get us volume?
No, you have to multiply by h.
Right. Okay, good. So we put it all together. So it's going to be the volume of the cylinder. It's going to be the volume of the cylinder with the outer radius minus the volume of the cylinder for the inner radius, or minus all the airspace, right? So that looks like this. It's going to be pi times 3 squared times 7. That's the volume of the cylinder for the outer radius, minus all the space, which is pi inner radius times 7. Okay? So now, we want to imagine, so I showed you one way that that cylinder can grow is by height. And so we're going to start with height. What's the rate of change of volume when the height is growing? Okay? So what we need to do is we're going to look at, imagine the height increases by, say, dh. Or we're going to do 0.4, and then we'll just, so suppose the height increases by 0.4 meters. How would we get how much the volume changes? And why do we want that? Because what would our rate of change formula be for volume as with respect to height? What would characterize, what's this big theme of the course so far that helps us understand rate of change, that would give us rate of change of volume with respect to height? What would that be? What little equation is going to characterize this rate of change?
dv is equal to dh times the rate of change.
Good. So hopefully some of you were thinking that, many of you were thinking that, and now that I write it, you think, oh, of course, right? This is what characterizes this rate of change. This is the rate of change of volume with respect to height. And what does it mean? Given any change in height, multiply by the rate, and we get the corresponding change in volume. So I just gave you a change in height. I said change in height is 0.4. If we can find the corresponding change in volume, then we'll know what m is, right? So we know our change in height is 0.4, and for that change in height of 0.4, we get the change in volume of this thing, then the rate should be apparent. That's how we're going to figure out what the rate is. Okay, cool. So if we change the height by 0.4, how much does the volume change? How do we find a change in a quantity? Well, one way we can think of that as final volume minus initial volume. So what's the volume after we change it by the height by 0.4 minus the original volume? And that'll give us the change in volume. Does that make sense? Right? You've been doing that a lot with function notation, right? The variation in a quantity is the final value of the quantity minus the initial value of the quantity. So we've got the initial value. Here's the initial value of our quantity. The final value will be the volume after the height is increased by 0.4. So what will the new height be? What will the final height be?
7.4.
7.4. So we're gonna find the volume of this thing when the height is 7.4, and we're gonna subtract the volume when it's 7. And that's this. Okay, so dv is the volume, the final volume when the height is 7.4 minus the volume when it was the original height. So just repeat this, right? Repeat that. Okay, is there another way to do this? Is there another way to get this dv? So increase the height by 0.4, right?
You do the integral from 7 to 7.4 and then put in that MDH.
No, because we're no, easier than that. Easier than that. So look, I just increased the height by 0.4, right? Didn't that just kind of like like stack on top of the original cylinder, just a new cylinder just like it?
So we could add like the volume of DH using this height in the original formula.
Right. We could just find the volume of this new chunk that I just set on top, right? And that the height of that is 0.4. So does that make sense? So that the change in volume would just be the volume of this new chunk of cylinder that I just set on top of the old one. So I can use pi r squared h, but now my h for that part is 0.4.
Could we have found the derivative of volume instead of, like, could we have found an equation for volume and then taken the derivative of that to find dV?
Maybe. It's kind of getting off track. Like it's kind of taking a long route to this, I think. But
Okay.
maybe something like that could have worked. All right, so here's another way to write that dV. Just take the volume equation and put in this height of 0.4. So these are equal. So these are both dV. But this one's a lot easier to work with, right? Because I got all this stuff in here and I had to simplify. So I'm just going to go right to this one, right? So this is the change in volume. It's how much volume of this new cylinder that I sat on top of the old one. And what are we trying to get this to look like? We're trying to get it to look like dV equals mdh, right? We're almost there. Where's the dh in here? 0.4. I can factor it out. It's in both. And what's left? Pi times 3 squared minus pi times 2.5 squared. And that equals dV. And this is dH. So we've got it, right? What's the rate of change of volume with respect to height? Looking at we've got dV equals something times dH. What's the rate of change of volume with respect to height?
Pi 3 squared minus pi 2.5 squared.
Right, this thing right here, that's our m. The rate of change. So the rate of change of volume with respect to height is what? Pi times outer radius squared minus pi times inner radius squared. Okay, here's a big takeaway. But what's that? What is pi times outer radius squared minus pi times inner radius squared? What is that in this figure? In this cylinder?
The shell.
The shell. What do you mean?
Is it the? Oh, sorry.
No, you go ahead. You can probably concise it better than I can.
It's the. Is it the surface area of that region?
Yeah, which region? Yep.
The filled one, like what he said, like the shell, but like. The
How about
area.
top, bottom, sides? It's the surface area of what? Of this thing?
It's the bottom of it.
Okay.
The bottom of the solid.
Or the top, right? Is the top okay too? Can we do the top?
Yeah.
Okay. So the light gray region, right? So this is the area of that light gray region there. Do you see that? So the area of that light gray region, or the area of the base of the cylinder, this is the area of the base. The area of the base is the rate of change of the volume with respect to height. Where is volume being added on here? Remember so where is volume? Looking at thinking about the animation. Boom, boom, boom. Where is area being added on?
Size.
On the sides?
Height.
No, the height, right? It's growing in height, right? It's growing in height. DH, we're adding height to this. So it's growing. Where is it growing? It's growing on the top. And what did we say about, we said this earlier with area, right? The rate of change is the size of the side where the stuff is being added. The rate of change is the size of the side where the stuff is being added. Where's the stuff being added here? If the height is changing?
On the top.
On the top. We're adding stuff up on the top. And what's the size of the top?
Constant.
Constant, the area of the base. It's the area of the base. So it's the same thing as signed area. The length of the edge on the right side, was the rate of change. That was the size of the side where the stuff was being added. Same thing here, the size of the side, in this case the area of the base, that's the place where stuff's getting added. So that size of that surface is the rate of change of volume with respect to height. This is making sense. So big takeaway here. If the cylinder is growing in height, what's the rate of change? The area of the base of the cylinder. So this is what we spent the last 10 minutes doing. If the cylinder is varying in height, the rate of change will be the area of the base of that cylinder. If the cylinder is varying in height, the rate of change we're going to use is the area of the base. In this case, pi r outer squared minus pi r inner squared. I'm saying this is really important, and we have quizzes at the end of class. Okay, any questions?
Yeah, and sorry, what you mean by the area is the base.
The base, this gray. See the light gray?
Yeah, that hollow cylinder.
No,
base.
the light gray area. The light gray area on the cylinder, not the space. Right?
Right. Yes. Yes.
Do you see that? So it's the area of this gray, light gray ring.
Yes, I understand.
Okay, cool. Other questions? Okay, but so that's the one case. That's the one case where the cylinder varies in height. Okay. The other case is where the area varies in radius. So let's investigate that. So this is the bottom of page 2 now. So now our cylinder is going to grow in radius. And recall that the volume of the shell is this, the pi r outer squared times the height minus pi r inner squared minus height. That's our volume. And so we're going to grow in radius. And so then what's going to help us get the rate of change? So what? dV equals m dr. This is going to be a new r. So let's go m sub r. So given a change in radius, the resulting change in volume will be the rate of change times that change in radius. So this is what we're after. Okay, so you're not going to have time to take the notes, so go back and watch the video to take the notes. So I would just really listen carefully to this little derivation, but we got to kind of move for time's sake. So, so here is the change in volume due to a change in radius. Just the outer radius increases by the dr. So here's the outer radius increasing by dr. Here's the new volume. Here's the old volume, right? So volume final minus volume initial with the outer radius growing by dr. So that's not so bad. So now notice that we got minus this, minus a minus, the same thing. Those go away. Right? So minus this and then ends up being plus this, which just leaves us with these two terms. Okay, so it's just that minus that. Okay? Opposite. And then when you multiply this out, the first term, pi times 3 squared times 7. So you multiply this, you're going to get 3 terms when you multiply out this binomial. The first term is pi times 3 squared times 7. Well, there it is. Those go away. So all you're left with is the second 2 terms, which is... Okay,
Yes.
so we saw that when this first term cancels out, so we're left with the second and third term in this expansion, which is 2 times 3 times dr times 7 plus pi times dr squared times 7. Okay, first term of the expansion cancels with this. All right, so I can factor out pi, I can factor out 7, I can factor out 1 dr. Okay, and so now we're getting dangerously close here to dv equals the rate times dr. So what is the rate? There's the rate. Okay, and so what happens? So we're going to so in order to get exact volume from approximate volume, we're going to let the r get really, really small. So this is still a little bit positive, but so small that we can just toss it away. So we need it to be a little bit positive when we multiply, but when we add, it's just so super small that it doesn't make a difference anymore. So we get rid of it. Okay, so dv equals mdr. So here is m. What is that? What is 2 pi? So our rate of change of volume with respect to r is 2 pi rh. What's that in this? What is that thing? What is 2 pi rh?
The height of your, or the area of the. It's the area of the side of the cylinder.
Right, exactly. It's the area of this lateral side here. It's the circumference, 2 pi r, the circumference times the height gives this lateral area. Where is stuff being added when the radius increases? Where's the stuff being added?
Lateral area.
On the lateral side, right? It's getting bigger. It's getting bigger at the radius, right? The sides are growing out. And what's the rate of change? The rate of change is the size of the side where it's getting bigger. The size of the side where it's getting bigger. So here's the second. In the second case, when the radius varies of the cylinder, when the radius of the cylinder varies, rate of change is area of the lateral side. These are the things we got to remember. When we have a situation where the height is growing of these cylinders, the height is growing, then the rate of change is the area of the base. That was case 1. When the radius is growing of these cylinders, the rate of change is the area of the side. But you can remember that because it's always the size of the side where the stuff is being added on. It's always the case with area and now with both these volume cases. Okay, so let's look at an example. Any questions on that?
Oh, I'm sorry. The lateral side is that dark green part?
Yeah. The dark green. Right, so it's the vertical dark green ring.
Okay, thank you.
That's the area of 2 pi rh. And that's the rate of change as the radius grows. Okay, so for any empty shell, what function would give the total accumulation of volume? So I want to, for any empty shell, for any situation, what would my volume accumulation function be? What would give a total accumulation? Hopefully you're thinking it. It's all the volume up until A plus
The integral
A to X of what?
of the rate of change times the height.
Rate of change of volume times dt, times a little change in X. Or this could be Y, all right? So our independent variable could be Y, but just we'll start with X. So we know if you have the rate of change of volume, you can set up an integral to get the accumulation of changes in volume plus all the volume that's accumulated from before. That'll give you the total volume as a function. Okay, so now let's look at this example again. This is where I rotated the sine curve. This is sine. I rotated it around the x-axis. And then we're going to fill shells like this. This is how we're going to fill it up, with shells like this. So here's the big question, okay? Everyone paying attention. How are each of these cylinders. We're using cylinders to fill up an empty shell. How are the cylinders growing? Are they growing in height? Are they growing in radius? Are they growing both ways?
Radius.
Radius.
So, without being mean, wrong, okay? So look at the pink in the current interval, at the current value of x. You're looking at the pink cylinder. How is that growing, in radius or height? The pink cylinder in the current interval.
Only by height.
Only by height. It's only growing by height. Okay, and that's the key. To figure out if your cylinder is growing by radius or height, you look at what's happening in the current interval at the current value of x. You don't look at surrounding cylinders. You don't compare cylinders. You look at the cylinder in the current interval. How is it changing? Just the height is growing. And then you go to the next cylinder. Its height grows. Do not compare cylinder to cylinder, adjacent cylinders. That's not how you determine how the cylinder volume is varying. You look at the current interval only, at the current value of x. These cylinders are growing by height only. Does it make sense? Because in the current interval, as x increases, the height increases and the radius stays constant. So what's our rate of change of area in this case? Area of the base. When the cylinders, remember, area of the base. When cylinders grow in height, don't compare to other cylinders. Just look at the cylinder in the current interval. When it grows by height, then the rate of change is the area of the base. What is the area? So this kind of this dark, this olive green. What is the area of the base? That's just pi r squared. It's just the area of a circle. What's the radius of that circle? Radius is, well, the value of the function, right? It's the y value of the function. And what's the value of the function? We said it was sine x. So we got it. And our volume accumulated at the beginning is 0. So v of 0 is 0 plus integral from 0 to x. The rate of change is the area of the base because the cylinders are growing in height in the current interval. The area of the base is pi times sine of x. T, use t now, squared dt. So there's our volume accumulation function for this thing filling up as x increases from 0 to pi. If you want to get the volume of the whole football, v of pi. Okay, so I did a lot of talking there. Any questions?
I just missed that last part. So the v of pi, how is that the volume of?
Because we're accumulating. So these are the x values increasing here. So right now, whatever this value is, say it's 2.1, then v of 2.1 is all this volume so far. It's a function, v of x, right? So then as x increases, we get more volume until we get to pi, and then it's all the volume inside the shell.
Oh, right.
So then,
because it's a sine function.
so v,
yeah.
right. So sine is halfway is pi. Okay, questions on this volume accumulation function? Remember, if the cylinder grows by height in the current interval, then the rate of change is the area of the base. If the cylinder grows by radius in the current interval only, then the rate of change of volume is the area of the lateral side. Okay?
So is it that if it's the x-axis that it's been rotated around, it's growing by height?
Don't know. There's going to be so much in these
Okay.
problems. Don't try to make up rules like that. We're going to do
Alright.
every problem individually and talk it through. You start making up rules, there'll be an example that violates your rule, and then you're in bad shape. Okay, go take your quiz. Go take your quiz and have a great weekend. Look for new homework for next Wednesday on Canvas. And have a great weekend. I'll stick around after the quiz for questions.